some data and interpret the results in it. So in the beginning we start, as you know, this whole thing is also an introduction to R. So we start with the first exercise, which is load the data. So it's really just reading in the data into R. And then just having a first look at the data set, how it looks in R, and how you get the first information and to just have a look at it. Then we're going to do some plots and summary statistics, another scatter plot, some more summary statistics. So this whole thing is summary statistics and plots. And then we're going to estimate the linear relationship between consumption growth and income growth by least squares. And for that we first talk a little bit about the least squares method, what that's all about. And afterwards we're going to interpret the coefficients and then interpret the R square, which is a measure of fit, which can help us discuss a little bit about the goodness of fit of this model that we estimated. And then if we get to it, the next task will then be a simulation study, which is also meant to showcase how to construct a simulation where we're just simulating a chi-square distribution. Of how we get like this. And I'm always going to switch that. There are some exercises where we want to develop them and give you the code, but as I've already uploaded the code, there are also code chunks which I'm just going to run and discuss because they're, I think, too long or not really important enough to really go through it very slowly. Okay, so as I said, the first part here is going to be loading the data set. Loading the data set in R, and this is, even though it sounds very mundane, this is always one of the things that people tend to struggle with, because if you can do it, then well, you can't even start to work, but there are just some things that might get a little bit annoying and tricky. So the first thing that I would always recommend you to do before even intending to load anything into R is look at the data you're provided or that you downloaded somewhere. So there's different ways to get to data in R. One is, in some packages there are already data sets provided, which you can just load in R, which is very nice. This is, for example, the data set that is used in the lecture. Right? So this is a data set that is very well known, the Boston, what is it called? Yeah, some Boston housing data from the 70s, so that is used in all kinds of packages. So they actually provided, and it's open source, so they actually provided in the R package. Very easy to get to in R. We are obviously going to give you data the most. There are sometimes going to be CSV files, there are sometimes going to be Excel files, and you need different kinds of functions to load them into R. So as always, Google is going to be your friend. This file that I uploaded here is a CSV file, which means that it's comma-separated values, and it depends on how they are separated, the entries are separated, how you want to read it in. So this is why I would how the separation works. This is a set, here, very simple CSV file. You have the first row, which gives you the names of the data columns, and they're separated with semicolons, the same as all of the data. So here you see you need the separator as a semicolon, which is typical in German data because if you have comma-separated values and mix that with the German data format where you have a comma separator as a decimal point, then, well, that's not going to work out, right? So this is why in a lot of German data, you have semicolons, and then the comma is a value for the decimal point. Well, here, this is kind of a weird data set where that is mixed, right? So you have a semicolon as a separator and a decimal point, actually, so that's really not needed, the semicolon, but well, it's that way. And it's important to note that when loading, to know this when loading your data. Okay, so this is just one thing. And then, well, let's start. I'm going to give this some name, data income, because this is data on national income and consumption from the US. So income data, and then the one I can remember as read CSV, and you already see that when you type in, for example, in RStudio, it's also going to recommend a couple of different functions for you already. So the ones that are present. So the easiest one is the CSV, which is right, and you can also already see a little bit of notes. So you see that, for example, that the read CSV has as the default value for the separator a comma, and has for the decimal point a dot, right? So just a dot. And then you can also have a look at the CSV2, for example, where you can here in the CSV2 see that the default for the separator is a semicolon, and the decimal point is a comma, right? So in our case, where we have both of this mixed, it doesn't really matter which one you do have to adjust, right? So the read CSV2 is going to give you a weird data input, and the read CSV is going to give you a weird input if you don't specify your separator or your decimal point. Whatever you use, it doesn't really matter, but it's important that, so this is one of the reasons why it's important to just check. I usually use read CSV, and this is really personal preference. And the first entry in the function read CSV is the path of, so tell R where to look for the data, right? So in my case, I don't have to enter a path because the data file is in the same folder as my notebook or my R script. So here in the data folder, info notebook, opening. I have in the intro RMP file and the data file. So this is why I don't have to specify the whole path. If you don't have it like this on your computer, you have to specify the whole path, and you get the path. And I don't want to do in all of the code I give you. I don't do this because, well, for one, it's different from Windows users to Mac OS users, so it doesn't really matter. And also, you're not going to have the same path as me, so if I give you my code, you can't run it if you don't change the path. So you really have to figure that out yourself. For Windows users, which is here, it's really nice, I think. Or, I don't know, does it work here? No. I think you get the path very quickly, but now I can't find it. But a backslash for these paths. So yeah, but as I said, this is going to be different for people using different systems, so I'm not going to go into this too deeply. Okay, so this is what the path would look like if I for the notebook would look like. Okay. So as I have the file in the same folder as my the data file in the same folder as my markdown script, I can just give it the name. So in my case, it's called Ü1 CSV. And now, because I picked the read function and my separator is not a comma but a semicolon, I also have to specify that like this. Okay, and then I can run this, and now I have my data set in here. And now there are multiple ways of looking at it. So here we'll have to just have a quick look at first the data set. I think the one thing I always do first is just open this data set in the global environment, because there I actually see everything already. If you actually want to print it in the console, that's also fine, but I think this is very nice. That already gives you a very nice overview. So here in the global environment, you see that we have 284 observations for 3 variables. The variables are called year, GDI, so gross domestic income, and cons, which is for consumption. We start here. The year is noted as a character, and it starts, which just means a string of variable of some anything, right? So character can be anything in R. It's just a string of stuff. So it can have numbers, it can have whole sentences. So characters are very, very fluid, but they're not numbers, right? So they're characters here. It starts in the data starts in 1947, Q2, and yeah, GDI and consumption are numeric data sets with like 1.34, 3, 2.45, which means that we have here a data set in percent. So this is a data set in percent. So in 1947, Q2, the GDI of the US was 1.33%. So it's growth, sorry, growth. Yeah, it's GDI growth. So it's 1.33% growth in the US there. Okay, so obviously there are also ways to just have a look at it manually or get some of the information manually. So for example, if I want the names of my data points, I can call for the column names with column names, and you already see it. I mean, this is nice. The nice thing about working in development environments is that they give you a lot of information. If RStudio would have a generative AI integrated, which it doesn't have, it would actually propose already stuff that you could do. So this is what's then very nice if you work in for example, in VS Code, where you have a generative AI implemented in the development environment, and then you can, it already gives you ideas of what you could do, right? So you don't have to review it ideas yourself, which is crazy working. But yeah, so the column names of what I did is called data, called data income. And the first 6 rows of the data frame. This is the header. So we have you can also use the function view, for example, view data and then it's going to open up the whole data set here, and you can scroll through all of the observations. I think this is a nice thing because there, if you scroll through, you can very easily see if there are any data points missing. And obviously, I am giving you a very clean data set with no missings, but if you work with real data, there are always going to be issues. So this data cleaning process in the beginning of starting to work is actually one of the main contributions a lot of people make. Because, one of the, if you decide to do, for example, an empirical method thesis, I would guess in a lot of cases, a lot of the time spent on your master's thesis is spent cleaning and actually getting data to work in at all. Okay, so this is just the first look. Now let's get to some plots, and I don't want to type in all of the plot details, so this is why I am going to switch to my already produced solutions. Because with the plots, I also want to talk about the plots, actually, let you think about the plots a little bit. So, here we're supposed to plot a line plot of both variables into the same plot, use different colors, and add a title, a legend, and dates in the x-axis. Does the plot imply a relationship between the two variables? That's the question here. And for this, obviously, to actually be able to think about what kind of plots are sensible. For example, a line plot is not very sensible in all of the cases with all of the data. But in this case, we gave you a ordered data set because it's ordered by date, right? So it's dated series, we have a time series here. So here, a line plot is very nice because you can observe actually the same variable over time. And if we now plot it just as a line, we actually get sensible information. If you would plot a cross-section as a line plot, I would guess it doesn't really look very interesting because nothing's going on there. Okay, so there's a lot of stuff here. I just want to note some things. In R, it's important. Right now, we have year, so the data series as a character. We cannot give this character into any function for the plots because it wouldn't understand what to do with it. So what we have to do first, or what we always have to do if we work in time series, is to convert this character series into an actual time variable where R understands that this is an ordered time series, right? So this is what's going on first, convert columns with dates into class year quart. So this means it's a year quarter series. If you have any other kind of date series, you can use different forms, and you need to use different classes. But in this case, we have this year quarter thing. For monthly data, it would work differently, as I said. For daily data, it would work differently, and so on. So this function is actually not provided in R as it is. So the most important thing is, if you want to run the code, one of the first things you should always, you do have to do is load the package. So the package for this is the zoo package. I think I already loaded all of my packages, so it doesn't matter. But just if this function doesn't run for you, then this will be one thing that you didn't load the correct package. Because this is something, and this is what makes R good and open source and interesting, is that there are some features provided already in the statistical language, but you can, like the whole R community for years and years and years has added on whatever they needed and also provided to others, right? So, and this is then classes and packages. You can always write your own function and publish it in a package so that others can use it. Okay, so the package is going to give us this. And then we can use this to then, we're going to need it for the plot. The plot here, I use the simple R plot functions. There are many different other ways to plot in R, right? So there's ggplot, this is a whole other category of plots. You can use whatever you want. I just wanted to show you the easiest, so the ones that are actually provided in R, and I also think that they already look quite nice. So if you work in different kind of data, then ggplot is way superior. ggplot2 is way superior to what I do here, but for this very simple thing, I think our base plots are fine. Okay, so we have the plot function, and then because we want to plot, we have to first provide just one data series. So I picked the GDI, and I call this data series by writing down the data frame it is in, so data income, and then the $sign, and then the variable you want to attach. So a data income $sign GDI, and because we want to plot it by time, right? So a line plot in time, we're going to plot it against the year series that we converted into that we already converted into a date, right? So now we can do this. Then I call the type of the plot I want to do, and the type is just a small l for line. This gives you a line plot. And then I already add the title and the axis. So my axis labels. And what I also already do here is to specify how thick the line is supposed to be. So this is, I picked a tree, and you can play around with it. All of these things now depend on how you want this plot to look like, right? So there's no right or wrong way to do a plot. I would say there are better ways to plot things because plots are meant for other people to look at them and understand what's going on without you having to explain everything, right? So they're meant to visualize something simply. So this is what you want, but how that actually looks like really doesn't matter. As a default, this plot line is going to be black. I could add a color here, a different color than black, but this one's going to be black. The next line is then going to be blue. So we have two different colors, but you could also give the first line a different color. So you could just all of the color names, you find them online. Okay, so this first thing is going to produce the plot, and now I want to add on to this plot. And in our base plot, it's easy because you just have to write it below the plot, and then you run everything together, and then it's going to all be in this plot. But the first part is the plot function. Now I'm adding onto this plot a line, another line, so lines, and this is going to be the line for the consumption growth, which is also plotted against here, also has type L, has color blue, and has line width 2. And so this is the next thing. Then this is personal choice, I would say. I'm going to add a grid to this plot. You don't have to do this, but I think a grid is always kind of nice to be able to judge how the plot is going. And then I add the legend with another function legend, and then I can what is the name, what are the names in the legends, what are my colors, what is my line width, whatever, right? So this is all very up to you how this thing looks, but this is kind of everything I add. The annoying thing, I would say that some of the things, it's important that they're in the right order, and other things not, right? So the plot function always has to come first, but I would guess lines and grid can be separated, and legend maybe also, but sometimes legends have to come last. So this is then, yeah, you have to figure that out when you do your plotting, but just as a heads up that this is this order that I have here is not all of the things unnecessarily have to be in this order, but yeah, some of them want to. Okay, so now I ran the whole plot, the whole thing, and the first thing that happened is that my year variable turned from a year class to a 4-year class, and now this whole thing knows that we have the 1948 Q2 as one year variable. Okay, and now this is how the plot looks like with my title. Let's see. With my title, my axis, and the dates on the x-axis, and my legend, which is in my case inside of this plot on the right, top right hand corner. As I said, play around with this. Okay. Yeah, as I said, for time series, these line plots make a lot of sense. But and we can also maybe look at it or can tell something about the relationship already. So the question for you now, does the plot imply a relationship between the two variables? If you look at this, would you say maybe a show of hands who think there is a relationship? Maybe who thinks there's no relationship? Okay. Then all who voted are in favor. Yeah, I would also guess. So I think in this plot you can see that high income and high consumption go sometimes hand in hand. Low income, low consumption also go hand in hand. And I think, growth, low income growth, low consumption growth both go hand in hand. So these variables move up and down in the same way. So I would assume that there might be a positive relationship between both, which kind of also makes sense. So another plot we could look at is the histogram, which just gives you a histogram. I'm just going to produce this, so the function is hist, and then you have to just enter the data that where you want the histogram of, and then you can play around with it. And there's labels that you can do. Then a title. Then in the histogram you can decide how many classes. So how many classes you want to do. Play around with it, and you can also change the color. I think the default color is also okay. So let's just run this. Here. So this is the histogram for the gross domestic income growth. Mostly and you can see a little bit the distribution of growth rates. So most of the time the GDP And then there are some negative values, but not so many. And then consumption growth has a very similar look to it, so it also has this positive, a lot of observations in the positive realm, a few outliers of very high growth, very few outliers of very low growth. So, histograms. Next, how to obtain some summary statistics. Yeah, as I said, I'm not going to write all of this down, but I just wanted to also have you have just have an overview of what some simple things you can do. So, okay, the summary statistic at higher moments, quantify the visual conclusion including the histogram. So everything we see in the histogram can also be seen in just looking at some numbers. So this is a choice I made. You don't have. You can do it very differently. So if you do this yourself, yeah, this is always like in most cases, the way I do something in R doesn't have to be the way you do it in R. So you can get to the same result in multiple different ways. It's, what I did here is to be very quick in doing this. I just took my income and consumption variable out as and produced a new data frame because I'm not interested in, and the reason is because I'm not interested in the summary statistic for my date series. I mean, what is the average of my date series supposed to be? That doesn't make sense. I mean, that's not interesting, right? So why even look at it? So this is why I produced a new data frame for my GDI and consumption growth. Then there's a variable the function summary, which is going to give you the minimum, maximum, first quartile, median, third quartile, mean data. So a lot of summary statistics already. And then I also want the covariance matrix to get also a summary of the linear relationship between these two variables. And because I'm also asked to do the higher moments, I also calculate skewness and kurtosis of my data. So you can, the question or why to look at skewness and kurtosis, by looking at those values, you can always see a little bit if your data is normally distributed, or if it does is normally distributed, or even symmetrically distributed at all, right? So let's just look at it very quickly. So here you see this first part, this first table, this is the output of the summary statistics, where you see the minimum value, the maximum value, everything in between, median and mean as averages. And then the next table is the covariances. And as we already saw before, there's a little bit of a positive relationship between them. Just also remember that in this covariance matrix, the main diagonal has the variances of both variables. So we also get the variance of GDI growth and consumption growth, and then the covariance between them. Then the next part is the skewness, which is 0 in GDI and 0.4 in consumption. Both are positive. GDI growth skewness is very close, I would say kind of close to 0, so this would be the 0 would be the value you would expect in a non-distributed variable. So GDI growth looks more, at least a little bit more normally distributed than consumption growth, but say anything about it. Do some tests, but yeah, this is already an indicator. Consumption growth might be a little bit skewed. And then And then always these kurtosis-skewness stuff, I would say you can interpret them in comparison to a normal distribution and also in comparison to other distributions of variables that might be comparable, but just by looking at just one of them and not comparing it to everything, I don't know if 8 is a large skewness, right? So that doesn't really mean anything. It's larger than the normal distribution skewness, and it's also larger than the skewness of the GDI, but there might be variables that have a way higher kurtosis, so yeah, or skewness. It doesn't really, on its own, I would say it doesn't. But in comparison to other distributions, we can. Okay, so now to the more interesting part. We have a closer look at the relationship between these variables, and for that we are going to produce first a scatter plot, where we then can actually see the relationship. Because in the line plot we only saw that they kind of moved similarly. Now the scatter plot is going to really show us if a high income also has a high consumption, or if a value with a high income growth also has a high consumption growth. Okay, again, the plot is actually very simple because we have the same function plot. Then we plot now income against consumption against income. Yeah, and we do the label. So on the y-axis we're going to have consumption growth. On the x-axis we're going to have income growth, and we have type, right? And in this case, in comparison to what we did before, is that I don't specify the type because the scatter plot version is actually the default type, so I don't have to specify anything, compared to the line plot where I do have to specify that I want to see a line, right? So all of these functions always have defaults, and if you need the default, you can just leave it out. Okay, so this is the scatter plot, and you see the default here is going to be these kinds of dots. If you don't like these dots and want different dots, you then have to specify this, and there are a lot of different options for this. You can do stars, you can do crosses, I think, you can do X's, you can do built-in dots, you can do whatever. And you can also give it a different color. So I use the default black. Okay, so this is the scatter plot, and here what we saw before is again also visually, and we can confirm, I would say, that we see this slight positive relationship between income growth and consumption growth. And now, I mean, this, also no. This is now a little bit random why it's asked here, because it could also be in the summary statistics. But the next part is compute the correlation matrix between the variables, which is just going to give us the standardized covariances, right? So correlation is just a standardization of the covariances, which gives us information on the linear relationship between two variables. And yeah, so we get this matrix. On the main diagonal, we have the covariance of the variable with itself, with the correlation of one variable with itself, which is by default 1. So by construction, always 1. And then on the lower left-hand corner, we have on the off-diagonal elements, we have the correlation between the variables, and you see this correlation matrix is the same as the covariance matrix is a symmetric matrix, because the covariance, so the linear relationship between consumption growth and income growth, is the same as between but as always, I would say even interpreting actually the size even of a correlate, I mean the size of the covariance isn't interpretable at all, or you can't really say this is large or small because it depends on the scaling of your variables, and the correlation on its own, one correlation on its own is also not so informative, I would say, because 0.68 might in some cases be very large correlation, but there might be variables that are way more correlated and there might be variables that are less correlated, right? So it really depends on what you're doing, right? So I don't know if I would say this is very large. It's on the larger side. I've seen smaller correlations. Okay, so now we get to estimating a linear, or to actually making doing a model here, because everything we did before was just look at some plots and some statistics. Now we want some statistical way of judging this relationship a little bit more. And to do this, we want to estimate a linear model where we regress consumption growth on income growth that relates consumption growth to income growth with the least squares method. And for that we're supposed to discuss or describe, what is it? Describe the least squares method. So I would say the easiest way is to look at a plot, or I will look at a plot. I'm going to upload my notes, so you don't have to take pictures or anything. And just a very simple plot where we have a positive relationship, like the one that we have here in our example of growth and consumption. Maybe I also call this growth and consumption, consumption growth. And income growth. And the model is consumption growth is probably going to get some intercept. Beta 1, and then some beta 2 times income. And then, because obviously not all of our dots fall directly onto the line, onto this linear function, there's going to be some error, E. And now the question that these squares, and we want to estimate this line, these, where we need the parameters beta 1 and beta 1 and beta 2. Now the question, so we want to estimate some line. Like this, which then would be consumption plus the estimator for beta 1 plus the estimator for beta 2 plus income. Right, so this would be this line that we're searching for. And the least squares method gives us a way to find this line. And the idea of the least sum of all of these errors, or the sum of all of these errors squared, should be minimized, right? So the distance between my actual data points and my line that I estimated should be as small as possible. How this is least squares is one of the ways to get there, by squaring all of the errors, adding them up, and minimizing this sum, right? So in the end, I would get some line that is, on average, the one that is closest to all of my observations, right? We square the errors because otherwise we would, positive and negative errors would cancel out, right? So that we don't want that. They're not supposed to cancel. These two errors are not supposed to make themselves smaller, each other smaller, doesn't matter. So we square them, because if we have them squared, then they're all positive, and we're going to get the same result. Okay, so what we want is that the sum of all of these errors, the squared errors, is minimized. So we call this also a loss function, the loss function S of beta. So E, the errors are going to be a function of my parameters, and we're minimizing them. So in the end, it's an optimization problem that we have here. And we're using optimizing methods to get there. So the nice thing in the for the least squares method, with all of the assumption of the linear regression model, is that we are going to get an analytical result for this in different methods and for different models. We're not going to get an analytical result, but we all know from math that we don't need analytical results. We can also use other methods, other solution methods to get an estimator. So Gauss, some Newton-Raphson, for example, stuff like this. Okay, so this is kind of the idea, this minimizing this function, and as I said, why is this a function of beta? Well, because we can just rearrange our function for EI squared to be consumption minus beta 1 minus beta 2 income. Right? So now this whole thing is a function of the parameters, and we can optimize in favor of the parameters. Just as a reminder, how these parameters, how this estimator looks like. So this is the ordinary least squares estimator. Ordinary because we assume all of our standard assumptions. We're making all of the standard assumptions we discussed last week, and LS for least squares. We also have generalized least squares, which has also the same idea in least squares, but just relaxes some of the assumptions that we have to make. But yeah, the estimator would be the same actually. Okay, so OLS, the estimator for beta 2 hat is the sample covariance between my two variables, and I'm writing now x and y because I don't want to write consumption and income here. I hope that doesn't confuse you. Right, so this is the sample covariance divided by the sample variance of x. And so you can also write that the sample covariance of x and y divided by the sample variance of x. So actually the estimator is also just a different normalization of the covariance where we relate the relationship between the linear relationship between x and y by the variance of x. covariance by the standard deviation of x and y, the product of the standard deviations of x and y. Right? So there in the correlations, the denominator also has the information on the variance of y, and the OLS estimator doesn't. And then we get the OLS estimator for beta 1, so for the intercept, which is just y bar minus beta 2 hat minus x bar, which has the nice or interesting feature that you already see that is always by design that the point of our means, the mean point, so y bar, x bar, actually directly on the regression line. This is always going to be the case. We can see it in the function of our intercept. And this is here the intercept, right? This is the intercept. And this will be slow. Yeah, I mean, I hope you all familiar with linear function. Okay, any questions for this estimation method? Good. Then we can go on to estimate our this model here. And let's do this here because this is a very important one. This is a function that's always going to come up because actually okay, you can, the LM function in R can be used for different kinds of model. LM stands for linear model, but it's very flexible on what you actually do. So in the end, I think most of the times when I estimate anything, when we're going to estimate anything here, most of the time we're going to use the LM function. So how do we estimate the model? Well, as I said, the function is called LM. More. LM, and then it's very simple. We just write the variables that we use. So in our case, consumption is supposed to be the dependent variable that is first. So we really just write the function, the model form that we chose. So in this case, it's consumption, which is then related with this swivel thingy to income growth, and then I need to tell R which data I'm going to use, or which data set I'm going to use, and my data set is data income. And it already gives you, I mean, this is the same. It's not the same in all environments. So now I estimated the model, and why didn't I save it? But if you just estimate the model, this is you get the call you chose, and you get the coefficients already. So what we see here already is that our intercept, the beta 1 hat, is 0.6, and the slope coefficient beta 2 hat is also 0.6, which is the coefficient for GDI. So we could also already interpret these numbers, obviously, but we want more, which is why I'm going to save this whole model thing as linear models. Okay, you can call it something else. And then if I run this, then this linear model is going to come up here on the right hand side in my environment, and you see that it's a list with 12 entries, and we can maybe have a very quick look at what we get in this, what is in there already. We get the coefficients, we get the residual series, we get some other stuff, we get the rank of the matrix, and some other stuff, fitted values already, quantiles, blah blah blah, with our degrees of freedom, yeah, lots of stuff that we might want to use. And all of the model already, so yeah, so this is interesting. But the output that we're usually interested in is the summary. So our summary statistics of this linear model. So let's just enter it here. Okay, so this is how the summary statistics look like. So you see you get a lot more information than before. So you get again the function call, you get some data on the residuals. So just some summary statistics for the residuals. You get information on the coefficients. Here you get the estimate, so 0.64 and 0.60. Then in the next column you get the standard errors. And then you get a test, a t-test, for the null hypothesis that the betas are 0, right? So the null hypothesis of this test, maybe I'm going to enter it, so in the output are R gives you a test on the null hypothesis that your beta is equal to 0. And it's a two-sided test here, so the p-value belongs to a two-sided test. Okay, just to be clear here. So this is what's going on here. Then you get other stuff, you get the residual standard errors, so the standard errors of your residuals, so more information on the residuals. You get the R squared, you get the adjusted R squared, an F test. This F test is a joint test, t test. This is important because this is the stuff I'm going to give you in the exam. So this is the output I'm going to give you in the exam, and you can interpret everything. So you should know all of the stuff that's going on there. Okay, so this is the t-test. And you also get the f-test for the null hypothesis that in this case it doesn't really make sense, but it's a joint test on all of the coefficients, at the same time. So you get beta 2 is equal to beta 3 is equal to beta k is equal to 0. So this is the null hypothesis, and against the alternative that at least 1. and the S statistic here, 248.7. These are related because they're both hypotheses are the same. We just use different test statistics, but these two are related in a way that the t squared, the F statistic here is the squared t statistic. So 15.77 squared is 284.7. And this is always going to be the case in the simple linear regression model, that these two are, I mean, those are two different tests for the same hypothesis. Two different, yeah. And about testing, we're going to talk about testing at length in a different tutorial. So if you're not familiar or if you don't remember any of this, we're going to go through this, all of this. I just wanted to make sure that we go through the whole output here. Okay, and now the point is interpret the estimation coefficient. Is there a significant relationship? Okay, that's for you again. So what's the interpretation of this 0.64 estimate for our intercept? Remember, we are relating here consumption growth to income growth. In this case, if there's no income growth, we would still assume that consumption grows by 0.64 percentage points. Okay, so this is, and this is highly significant. So, and yeah, as always, the intercept interpretation in most cases isn't really sensible too much. But yeah, we need the intercept to make a nice line. So what about the slope coefficient 0.6? What does that tell us? Very almost. I mean, and you did exactly. No, it's good. Yeah, kind of. And now that's a very nice way for me to be able to talk about this now. Yes, you said that the 1% growth in consumption growth, 1% consumption growth gives us 0.6% income growth. The important thing here is, and I hope to be able to illustrate it in a moment, is that it's actually not percent growth, but percentage point growth, which is because both of our variables and percent. And it does always sound a little bit tricky or a little bit like I'm not so important, but I think it's very, very important to know what, if we're actually talking number of percent or percentage growth or any or percentage points or anything else. And just as a very quick illustration, and it's not bad. I mean, most of the people do make this mistake, and most of the journalists don't even know the difference. So in any article, you will see this all of the time. So it's really like one of the commonest things. And I actually prepared an example to be able to illustrate what's going on and why this is important. Okay, just as a quick percent versus percentage points, and really just a very quick example. So if you have 1% income growth, and in the next period you have 2% income growth, this is a 1 percentage point increase, but it's a 100% increase, right? So this is obviously very different. And the important thing, or where it really gets then tricky, is when we compare this to a 10, when we have some growth of 10%, and that becomes an 11% in growth. Sorry. I don't know what I'm doing here. And 11%, then this is also a 1 percentage point increase, but it's only a 10% increase, right? So we go from 10 to 11, it's only also 1 percentage point, because percentage points is just the difference between the percentages that you're observing. And percent increases are actually how many percent of your base value you are adding in the next period, right? So in this case, in 1% to 2%, you're adding 1 percentage point, which is exactly the same as your base value. So increasing by 1% would mean you increase by 100%. But increasing by 1 percentage point would mean that you increase by 100%. If you're at the 10% value and increase by 1 percentage point, that 1 percentage point is only 10% of 10%. So the increase would then be 10% and still 1 percentage point. And in a linear regression where we regress two values that are already a percent on each other and just have the linear model, the interpretation is in percentage points. Yeah? So that's a little bit tricky business here. Because otherwise, the 0.6 that we have here, so which means that in this case, if we add 1% to every time, no matter at what kind of growth rate we already are, adding 1 percentage point always gets this 1 percentage point. But if we would interpret it in percent, the amount of percentage points we would add would depend on where, at what growth rate we already are, right? So the parameter for the 4% growth rate would then be different to the 2% growth rate, because 0.6% of 4 and 2% are two different things. But yeah, does that make sense? Yeah. So always, and really, if you make a mistake here, it is really the most normal thing. But I'm here for you. I'm here to hopefully get you to a place where you actually at least think about it or know that you have to think about this. Yeah. Okay. Then both of these, as we already said, both of these are statistically significant, which we can see by looking at the t-values. They are both very, very large. The p-values are 0, so we can reject the null hypothesis that there's no relationship or that both of these values are 0. So yeah, they're statistically significant. now, what is the definition of the R-squared measure? Is the estimated model a good model based on this characteristics? Okay, so the interpretation of this R-squared here, just as a reminder, R-squared is the relationship between the sum of squared of the model SSE divided by the sum of squared total. So it gives us a value, and this is the sum of the difference between our y variable that we have estimated and the mean squared divided by the sum of squared of the whole model, which is when we go back to my little plot here, is the question is how much of this whole error here can we interpret, is explained, of this whole error is explained by our model. So I'm not going to draw in there. Yeah. And in the end, it's nice because it gives us a value between 0 and 1 in the simple linear regression case, where we can then say how much of our total variation in the dependent variable is explained by our model. So it tells us, it gives us a value for how much of the total variation in our dependent variable is explained by the model. And in our case, it tells the R-squared is 0.46, which means that 46.95% of the this R-squared means that 64% or 67% of the variation of consumption growth can be explained by this very simple linear model where we regress consumption And now to this model you add another variable or two other variables. And then you check the R-squared. If the R-squared increases by a lot, then you say, well, then our first model wasn't so good, it can be better. If it doesn't increase a lot, then it's already fine, and you don't have to add the other variables. But this decision of goodness of fit should only be made in comparison to other models. In a lot of cases, especially in microdata, in large cross sections, 46% is a lot. It's really a lot. So I think if you check some of the micro paper, they're happy with the 10%, with explaining 10% of the variation in the model. And in a lot of cases, they don't even report the R-squared anymore because, if they're not really wanting to use it to compare different models, right? Where there's also other ways to do this. But the R-squared is still a very nice metric because it's between the 0 and 1, so it's normalized. It has this nice direct interpretation of this, how much percent of the variation in the dependent variable is explained by our model, so this is why it's still very, very nice. But so I don't know, 40% can be a lot or not. Okay, I only have 5 minutes left, and the simulation definitely takes a little bit longer to explain. So I would say we're almost done. I got a question last week about the homework, and I just wanted to just make a few things, maybe add something that I didn't say a bit more than last week. So for one, you don't have to do them, right? So they're not necessary. We just give you those points and a little bit of R on the codes, right? So, but if you really can do them or don't have time or don't want to, you don't have to. I would recommend you do them, but that is up to you. You do have to work in groups. So I want groups of 2 to 3 people. And as we get closer to the homework, because the first homework, I'm going to upload them in the end of November. And before that, all of that happens, I'm going to explain exactly how I'm going to hand in the homework, right? Before that, I don't think that it makes sense for me to talk about this now, because then in 4 weeks you're going to ask me again, right? So all of this, how do I upload, is all going to come up in November. I just want to say already, so if you can look for a group already, and then I'm going to provide groups on the blackboard where you can sign up with the group, right? And 2 to 3 people. Okay? So this is the important thing that you can do already. Other than that, I think the information is better to come closer to the actual homework. Okay. See you guys next week.
我的天呐，我的左骨又被卡断了一个，我的天呐，好像是那个 CJY， 我的天呐，上一个课真的是把命都要了，我的天呐。